So if we look at our failure curve, we talked about this at all the previous webinars, and we see this area where we're over here in reactive, where we find things out using human senses. Well, now today we're going to discuss, as we move up the curve, how to use these technologies that are available to find failures of equipment long before the failure reaches the point where it reaches those human senses areas, and at that point, there's no way to bring it back to new. So we'll look at some of the technologies today, some of the basic details. Again, if people are interested in longer training sessions, longer training webinars on this topic, just let me or Justin know. We can set those up for you, especially on the individual topics. But all of them are a very important part of a process in movement and reliability. So the ones we'll discuss today are these 6: oil analysis, wear particle analysis. We'll touch on that briefly. We're going to talk about vibration analysis, how it's used, and what kind of equipment we can use this technology on. The importance of thermography. We'll discuss mechanical ultrasound, which is one of the primary technologies I use at the facility that I came from. And this one here detects some failures at some really early stages, especially in bearings and electrical issues. And then we'll talk about motor circuit evaluation. I think I have a few slides at the end on non-destructive testing, but that one, there's one that's more common for your stationary equipment. But again, why do we want to look at predictive technologies? Why do we want to find things up farther up the failure curve? Well, first of all, we want to make sure we reduce collateral damage. And what that means is, let's say my vibration analysis technician comes in and tells me that I have a coupling that's misaligned, and we can tell that from vibration analysis. Well, if we do nothing with that alignment issue, we'll eventually take the bearings out on the motor and the pump. And that's going to be the collateral damage that happens from that coupling misalignment, not only the coupling wearing out faster. Or let's say oil analysis tells us that we have particles or moisture in our oil. Well, if we take the particles and moisture out, we keep the bearings and other components in that equipment from failing. So again, that reduces that collateral damage. The key point of using predictive technology is that now we can plan the work. So, we're 35% more efficient with our maintenance people when we can plan all their work. So if our predictive technologies are telling us that things are going to happen 3 months to 6 months down the line, we can plan the work and plan to do the correct maintenance. That gets us into having parts. If we can find failures of equipment that's going to happen in 2 to 3 months, now we can have the correct parts there. We can plan the work, have the parts on site without expediting parts. Now we can do precision maintenance because we're planning the work. This is something the company I came from did. We made the rule there that if you can predict a failure within 1 month, you were not allowed to stock the spare part. So we were able to reduce spare parts inventories by 30% at some major facilities in our company. It's more efficient use of your maintenance time because now they're actually doing work that's planned, less emergency downtime. The repair work we can do if we plan the work instead of doing it under reactive conditions. We can actually extend the equipment life, and it creates safer work conditions. So which technology, or what is the technology needed for the failure mode that will occur? And this is what we're really trying to do with predictive technologies. Some companies, and we made the mistake at the company I came from, we just started using all technologies on everything. We really weren't figuring out what is the failure mode we're trying to find. So, the process of RCM, which we'll have a training session on that later in the year, that's going to help us decide what technology to use, because RCM breaks our component failures down into actual failure modes. And we ask the question, is there a way to predict those failures? So listing the equipment and the predictive technologies available could also work. We'll look at a little slide of that as we go through. But, by listing your equipment and all the technologies across from them, we can find the most effective one for the failures we're looking for. But again, there's no silver bullet theory with predictive technologies. This is a question that's asked by a lot of corporate people. Is there one technology that'll work for all failures? And there's really not. You have to pick the technology that fits the failure you're looking for. So how do you know which one to use? We'll look at some of these today. But again, it all boils down to cost. Especially when you're using outside services for like vibration and thermography, if you're paying a technician to be there, so we have to know what we have in cost and make sound decisions based on what those costs are. And a couple of examples of that when you're looking at technologies and what we're looking for. it states here, oil analysis cannot detect coupling misalignment. So if you're looking for misalignment issues at your facility, the best technology is going to be vibration analysis, because that's going to tell us at 2 times RPM we have some misalignment issues. But vibration analysis cannot tell us if the additives in our lubricants are depleted. As we learned in the previous sessions, there's additives in there. The only thing that'll tell us what those additives are is oil analysis. If you're buying a thermographic camera, I've been at facilities where they said, well, my primary technology is thermography. Well, thermography that cannot detect a lot of failure modes, such as imbalance. Thermography detects the failures of heat when it's farther down the failure curve. So we have to be careful where we use this technology and what we use it for. And again, if you take mechanical ultrasound, we can find many failures that are earlier on the curve. Bearing failures, electrical failures, and leaks and things like that. So mechanical ultrasound is a good technology for a lot of different failure modes. So when selecting the correct predictive technology, we have to understand what specific failure mode you're trying to find. And this is a key point here. The cost of the technology cannot be more than the cost of potential downtime or the potential failure. So this is one of the ways we look at controlling cost. So predictive technologies are tools that allow for detection and correction of deteriorating conditions and assets before they lead to failure. And this is what we're trying to find. We're trying to find these failures way up the curve, sometimes just after the equipment is new, sometimes developing some baselines when the equipment is new, so we know when there's change. And this is what we're really trying to do with predictive technologies. We're looking for these slight minor changes that may occur that tells us something's going on. So let's first look at one of the technologies here, oil analysis. So what are we looking for with oil analysis? Well, as we pull our oil samples, we're looking for moisture, because moisture is one of the things that cause our lubricants to change into a compound that's not a lubricant anymore. We want to know if the oil's oxidizing. Remember in our previous training, as oil oxidizes, the pH goes up, the oil becomes a compound that's not a lubricant anymore, and it's going to cause our component to fail earlier. We said in our last training that additives are depleted. So as the additive package goes away, maybe our equipment life's going to be reduced by losing those additives. Particle counts. The more particles we have in our lubricant, and based on what the particles are, our components are going to wear at a lot higher rate. We want to know if the viscosity changes, because a lot of our equipment, that lube film is based on the viscosity at the temperature it's running at and other conditions. And as oil oxidizes, the viscosity goes up. And then if we're talking about mobile equipment, we're talking about gas turbines and things that run at higher temperatures, we want to know if the acid number is going up. So that total acid number goes up as the oil oxidizes. So our total particle counts. We talked about this in the last couple sessions here. As the particles go up, we're getting more wear. And these particles can be in different sizes. So oil analysis is going to tell us how many of those particles are of those different sizes. Now, how often do we perform oil analysis? Well, we discussed this before. It's sometimes, and at the plant I came from on our critical equipment, our top 10 or 20% of our equipment, we pulled samples every month. On other equipment, we pulled them every 3 months. And like it says here, there's equipment in your facility that you would never do an oil analysis on. But there's things we should do visually. Your operators or maintenance people should still be looking at the oil and its physical condition, maybe putting a couple drops on a piece of filter paper to see what the color change is. Sometimes you can see particles on the filter paper. And using labs. Now here in the U.S., we're very fortunate. I do this training all around the world. There's places I go, like in northern Canada, where it's not easy to get oil samples to a lab. There's other countries I go to where there's no oil analysis labs, even in the country. So I show them different techniques to use to test their oils visually. But again, for here in the U.S., we're very fortunate. You got companies like R&G Labs. You got companies like Test Oil up in the Cleveland area. They'll return, they get the results back to you sometimes in 24 hours. Test Oil is really good about this because they run their labs 24 hours a day. So if your samples come in UPS at 4 in the afternoon, you're going to have your results on your desk the next morning. So on critical equipment, this is what you want. We want to know right away what's happened. We don't want to know 3 weeks from now what our oil analysis results were. And make sure you establish some alarm points. What are you looking for? What's the particle counts? And how low can my additives get before I actually react? So again, failure modes for oil analysis, lubricant life reduction. So as the lubricant oxidizes, as the acid number goes up, as the viscosity changes. Lubricant contamination. Where's the contamination coming from? Is it moisture? Is the moisture from the process? Is it from ambient condition? Where are the particles coming from? And remember, how, like we talked about in the last session here, some of the particles come in your new lubricants. And are there other chemicals in your facility? Are there other chemicals in the storage area that contaminate the oil? And then what are we looking for? Equipment wear. What's the equipment made out of? You know, bearings, a lot of times you're going to see iron and tin numbers go up. Sometimes if they have brass or bronze retainers in there, you might see the copper number go up. What are all those metal components? What are all those things that you'll see in the oil analysis sample? Where do they come from? In order to know that, we need to know what your equipment's made out of. So here I put a typical oil analysis report. This is from a company called Oil or Test Oil, but lots of information here. We've got some iron and lead numbers up here, probably the lead's from a bearing retainer. We got some additives here, phosphorus and zinc, which are anti-wear additives. We see they're not being consumed as we go across oil analysis from right to left. You know, we can see our viscosity is not changing, so that's a good sign. If you go down here to your ISO codes, we can see as the ISO code goes up, the number of particles goes up. But also down at the very bottom line here, we see our moisture. You know, if you're doing this every month or two, we see our moisture levels going up. So when our moisture level gets up around to this point right here, we should probably be changing that oil or looking at a way to get the moisture out, because we can see that moisture is increasing, and as the moisture increases, our lubricant's going to change to something that's no longer a lubricant. Here's a sample right here where this company here, if you look down at the particle counts, we've let the oil get so dirty that it's maxed out the meter at the test oil lab. You can see they're all 9s on here. It's a 27, 24, 20, which means there's so many particles in here that it's maxing out the test equipment. But if we go back one step, when it's a 26, 25, 21, look how many particles are in here. There's nearly 15,000 particles larger than 4 microns or 14 microns in a 1 milliliter sample. Then you can see there's 653 particles here that are larger than 50 microns. This component here is not going to last very long. And you can see up at the top our iron numbers are going up. You know, our tin numbers have jumped to an extreme level. You know, you might see tin numbers around this 26, but look what they're up to, 4,000 parts of tin, high concentrations of iron. This component has went down the failure curve now. There's no way to bring it back. This oil should have been filtered back here at the early stage of the oil change, trying to get these low ISO codes. Now we've looked at how, with the predictive technology of looking at our oil analysis, but sometimes we may want to see what the particles look like. So we want to know what the particles look like. We want to know what the particles may be. What kind of, where are they pieces of bearings or gears? Are they dirt from the process next door? Are they dirt from your process? This wear particle analysis is going to give us that information. So this technology is called analytical ferrography. So we can actually see a picture of what the particles are. You can see, you know, wear pieces, rust pieces, other foreign material. So if we look at some slides here from analytical ferrography, the top 2 slides are metal particles that have been lined up on analytical ferrography based on size. So we can see some wear metal particles on the top 2 slides. On the bottom slide, the lower left-hand corner, you know, those are some 20 micron, 40 micron particles in that slide. Still too small to see with the human eye. But look, there's some other particles floating around this slide. There's some coal or fly ash particles, some really fine dust and debris. If you look at the particle on the right-hand bottom, that's a piece of wear metal. Could have come off of a gear or a bearing or some component in your system. And we got a picture of this now. That little piece of metal there went through something that has scrape marks on it. And this equipment, this is what we want to see. What are those particle counts? They're high. We might know they're iron, but this is what we look like. I can tell you here we have some high bearing wear or high gear wear when you start getting pieces off that are that large. So again, wear particle analysis, more expensive than oil analysis, but it gives us that physical, that view. Now, one of the things that I did at the plant I was from, I bought a little digital microscope. You know, I bought it, if you go online on Google, on digital microscopes, I bought one that only costs $400. It goes up to 400 power, and it's got adjustable from 50 to 400 power. But at 100 power, my technicians, we would put a drop of oil under the microscope, and we could actually see some of these things in our oil without sending it to the lab and without paying that $50 or $100 for that analytical slide. You know, a 400 microscope and some, they sell these little concave slides. You can put drops of oil from your equipment in there, and you can see these exact same things. And you don't have to do very many of those to pay for that. You can actually take a picture of it on the microscope and put it on an SDI card, and you can put these on your laptop then and show people what they look like. But again, a good learning experience for your maintenance people and a very, very cheap tool. Our next technology. And again, I tell people this is the one of the technology that every plant should have. You know, I started using this technology at the facility I came from in the mid-'80s when they first came out with it. And I kept buying the models as they improved. The newer model is the UE 15,000. It actually has a camera on it. It actually has a temperature sensor on it. And you can actually see your actual spectrums right on the screen. But this technology uses sound. So as a bearing starts failing, as a component starts failing, it creates friction. It creates a sound that can't be heard with the human ear, but it can be heard with these high frequency sound detectors. So if you look at the picture on the upper left-hand corner, here's a UE 9000. It has a probe on the front for finding air leaks, steam leaks, gas leaks in your plant. So it's basically looking for high frequency noise. Now, as you're going around your facility with this and you've got equipment running and it's very noisy, it picks up none of that low frequency noise from equipment running, but it'll pick up high frequency sounds from air leaks, steam leaks, things like that, and also pick up electrical faults in your electrical switchgear boxes. The bottom probe is the ultrasound 10,000, and like I say, they make a 15,000. This has got you just change it change the tool on the end, but now we're listening to bearings. And we can listen to sounds of bearings as they wear. We can listen to sounds of bearings as they need lubricant. And we can actually lube based on what this signal's telling us. So if you see the little bar chart in there, as that bar chart increases, what happens is it tells you the bearing's making more noise and it's in its failure state. But even when the bar chart gets up all the way over to the right-hand side, you still have a couple months to react. So this is how sensitive this equipment is on bearings. Here's what some of your charts would look like. Now, this happens to be a valve on a compressor, opening and closing. So the left picture is the valve when it's new. It's making a quick open and close. And then as this valve gets worse, so you can see it on the spectrum here, not only would you see it, but you could hear the noise. But it's a wider band, which tells us the valve is leaking by. So again, all kinds of information with this technology. So again, you can listen to individual bearings. You can listen to gearbox internals. You know, we can use it for lubrication. And I'll show you another device here that's a little cheaper we can use for lubrication. But you know, now we can tell how bad the components are, and we can tell if a component needs lubrication or not. Now here's a technician. You know, back in the 80s and 90s when we used this, I used to open up all the 480 boxes, and I would take the tool around the inside and listen for noises. Of course, when the new electrical safety rules come out in the early 2000s, you're not allowed to open the high voltage boxes anymore. So now we can take this tool with a little rubber tip nozzle and we can go around the seam of this electrical box, and you can see the technicians here is hearing some noise inside. We don't know what it is, but when you hear noise in electrical, that means there's something inherently wrong in there. But if we open the box in and look at the terminal strip inside, which they did with the camera here, you really don't see anything here either. Now I could take the tool and go around that connection and hear it, but now with the camera I can tell I've got a loose connection. So that loose connection is putting off some corona, putting off something to make a sound. And the tool can be used for electrical inspections on high voltage, on substations, a lot of different uses for the tool electrically. You know, so one of the things we can do here with the tool, we can find compressed air leaks, oxygen leaks, hydrogen leaks. You know, we can test heat exchangers, boilers, condensers. You know, we can use it on valves. If you have a valve that's closed and you want to know if it's leaking by or not, you can stick the tool on the side of the valve, you know, especially down by the bottom of the seat, and we can hear noise if the valve's leaking by. You can use it to check steam trap operation, you know, because steam traps cycle and actually make a sound as they discharge. Well, you can listen to all those sounds with the tool. Electrically, another great tool, arcing, tracking corona. all things that we can hear with this tool. So switch gears, transformers. At the facility I came from, we tested all of our dry transformers every month at 5 or 6 different points in the transformer. We could tell if something was going wrong with the transformer just by the noise it was putting off. But circuit breakers, junction boxes, all kinds of things electrically we can check. Like I say, you can find arcing, tracking, corona, many electrical effects. Now, mechanical inspections with this tool: bearings, lack of lubrication, pumps, motors, gearboxes, fans, compressors, conveyors. An example of a conveyor in a salt mine. I was in a salt mine about 1,800 feet under Lake Erie, and the guy drove along a conveyor and he listened to all the rollers on the belt conveyor just driving along in a little gator. And if he heard the bearings make a noise just from that distance, he would get out, tag them, and they would change those assemblies out. So lots of things we can do mechanically. And then these are different industries that use the tool. The automotive industry, railroad, aviation, the marine industry, postal service, chemical plants, all use these UE tools to find failures in their plants and find failures of their equipment components. One of the original reasons I bought the tool was the air leaks. So it shows here the size of an air leak on the left-hand column. And it tells here on the right-hand column, based on some cost up here, you can calculate your own, but it tells you what it costs per year for these leaks. So you can see a 1/4-inch leaks are over $9,000 a year. And if you even go down to a 1/16-inch air leak, it's $594. But how many of those would you have at a large facility? So these tools pay themselves back just finding and fixing. Of course, you have to fix them, air leaks at your facility. So an excellent tool to pay for itself. And then you can also use it if you've got other gases that you use at your facility. Here's an example at a refinery where the company used the 10,000 tool. They found 39 argon leaks, 178 oxygen leaks, 234 natural gas leaks, 238 nitrogen leaks, 417 high pressure steam leaks. And look at the air leaks at a large refinery, 1,444 air leaks. If you add the cost up on the right-hand side, there's over $1 million worth of leaks that were found at this facility that if they fixed them, they would save that much money. But they only had bought 2 of these $10,000 tools, so there's a huge payback here. Now, the newer tool, the 15,000, if you actually put in the air pressure and the line size and some other factors, it gives you a value of what the dollar cost is on each one of the leaks you're listening to. So again, another benefit of the tool and the new software is it's out. But again, big savings here. Here's the UE grease caddy. This is a tool you actually strap on a grease gun. And you can see the technician here has a magnetic sensor on the motor bearing. So what you see here happen on this thing when he puts it on there and it's in the red if there's some noise, as he lubes this little bar chart can turn to green. And then if you over grease it, it starts going back to red. So here you can actually put the exact right amount of grease in. You actually know if the bearing actually needs grease. Now, I remember I bought this first tool in 1999 at the facility I was at, and within 4 months, we'd cut our grease consumption back by 30%. We were actually over greasing everything. We were greasing things on time-based, and a lot of times we found out that the bearing didn't actually need any grease after that week cycle or month cycle. So again, a 30% reduction in grease just in 4 months. And now, we were using it to determine frequencies and volumes. Now, what we did is after we determined frequency and volume for our bearings, we didn't have the tool on there anymore. And then UE makes a new tool now that actually has more data on it. It's actually an analog tool that can show you what bearing you're at, how much grease goes in that bearing, what kind of grease, and it also records a little sound bite as you're putting the lube in. So lots of tools on the market like this that's going to improve your predictive results. Now, this tool works really well on equipment that's above 900 RPMs. When you get down below 900 RPMs, like you see some slow-speed gear pumps here that may only be running 150, 200 RPMs, this tool you have to put the headphones on. So you can see the 2 technicians in these pictures here. They have headphones on. They're actually listening to the bearing and putting the right amount of grease in. So again, some training curves around this tool, but very, very effective. The ultrasonic's a very, very effective tool. Now we get into another technology here, thermography. It's used to find failures due to temperature change. So as temperatures increase in electrical and mechanical components, the chance of failure of that component actually increases. So what are some techniques we can use? Well, one of the things I always like to teach about thermography is this term called emissivity. Well, emissivity is a reflective value of any surface. So if you have a painted surface, your emissivity is 0.9. If you look down at copper, it says oxidized copper has an emissivity of 0.7. Polished copper has an emissivity of 0.25. So what does that mean to a thermographer? Even if you pick up one of your little handheld temperature guns that you carry around your plant, and many of us have those, if you look in the upper right-hand corner, upper left-hand corner of that little temperature gun, there's going to be a little symbol up there that says E equals 0.9. And just about every one of those sold as a standard, there's the emissivity set on 0.9, which means it'll read a painted surface or a solid wall surface or a painted pipe surface. It'll read it accurately. But if you're looking at in a switchgear panel and you have polished copper, it's not going to be accurate because your reflective value is 0.25. So if you wanted an accurate reading on polished new copper, you would have to change the E value to 0.25. Now it's going to show a temperature, and even if you're looking through a camera, it's going to show a temperature. But if you want it to be an accurate temperature, you need to change that emissivity value. So this is just one of the things with thermography, where if you want accurate temperatures, if you just want to see temperature change looking through the screen, then all the cameras will work just fine. But again, the cameras, I remember the first camera that I quoted for the company I worked for back in the mid-90s was $65,000. So there was no chance that my company was going to buy a $65,000 camera. So we used outside services. But now cameras like these two here, the one on the left here cost about $6,000. The one on the right's about $8,000. They hold 500 and 1,000 images. The screens are pretty clear. So now with these cheaper tools, I could do more thermography at a more frequent basis. I remember we used to do them once a year. Then we started doing them twice a year. Then we started doing mechanical inspections. Well, as you do these inspections, those all cost money the more times you bring the guy in. So now I wanted to put these tools in the hands of maintenance people so we can do thermographic inspections more often, sometimes monthly, sometimes weekly, and the tools are available now to do that. Well, what kind of things can we find? If you look at the picture look at the right half of this picture, we see a terminal strip with the human eye, or the naked eye here. We don't see any change, but looking at it through the camera, we see we've got a couple hot connections here that need to be tightened or maybe replaced. If we don't do them, remember in thermography or on electrical issues like this, these issues are not going to go away. They're only going to get worse. But here we can make the correction. Some mechanical inspections. Here we see, just looking at this fan, we don't see anything looking at it. Yeah, maybe the maintenance guy could go up there and touch it. But with a quick scan of the camera, I see I've got a hot bearing on this fan. I can basically see what the temperature of the belts are, and I can see I've got a hot motor. Now, what's causing this? Does the bearing need lube? Are the belts too tight? I don't really know from looking at the picture, but it gives me some indication that I have a problem coming up. Here's a picture of an electric motor. The electric motor shows hot in the middle. If you look at the left-hand side of this electric motor, we see some purple there. That purple is the cooling air trying to go across this motor. But in this particular plant right here, when I went to the back side of this motor and I scraped all the textile material off the back of the fan guard where it was plugged, we cooled this motor down. We started seeing the purple go farther down across the motor, and we cooled the motor down. Now, a rule of thumb, for every 18-degree rise in the temperature of that motor, you cut the insulation life of the windings in half. So by cooling this motor down about 20 degrees, we actually extended the insulation life on the windings by 2 times. So again, there's a failure mode that we're actually looking for. Now, if you explain this to maintenance people and operators, that fan guard has to be clean and we have to have good airflow across that motor, and it makes the motor last 2 or 3 times longer, sometimes 4 times longer. I've actually done this at facilities and lowered the motor temperature 35 degrees by cleaning all the crud off the motor and off the fan guard. As people know about these failure modes, we can correct that, but it's easy to see here with this picture. Steam traps. It doesn't take anybody, it doesn't take a steam trap genius here to figure out which one of these steam traps is leaking by. And with a quick scan of the camera, I can see the one on the left is more than likely blowing straight through, where the other two have a temperature change on them, so they're probably working just fine. Insulation on it. This was a methanol column in Texas. Now, what do you think the issues are here? The metal jacket on this insulation or this tower look fine, but you can see the insulation underneath is probably bad. We got a lot of heat spots on there. The other picture is a substation at an Alcoa. It was an electric melting plant for melting aluminum, but look at all the hot spots in the substation. Are those issues? Is it normal? I don't really know. The picture showed that there's potential issues in this substation that could cause this plant some major cost. Easy to see, easy to find with a camera. So when you're using thermographics, what are we looking for? We're looking for changes in temperature from the last report. A lot of times we'll go out and do a scan, take some specific pictures, see what the temperature is, and then what are they next month and what are the week after. So now we can track data. We want set some alarm set points on specific equipment types. I remember the very first thermographic report that the guy brought into me at the company. The binder was 3 inches thick, and there was like 200 pages in there. And I said, that's the last thing I want to see is 200 pages of issues, but some of the temperatures were only off 5 or 6 degrees. So I made it clear to the guy. I said, I want to see, temperature ranges that are 20 or 25 degrees out of normal. And I want my report to be 1 inch thick instead of, 20 pages instead of 200. But I want to attack the big issues first. So as you correct those things, then we can take more pictures. We don't want to waste time with that equipment that's below that alarm point. And then if you have your own camera, this is a lot easier to do than hiring an outside service. We can do these things more often and see the trends. But we want to catch these. Just remember that my last comment on the thermography. Thermography is an excellent technology, but if you think about where you're going to see those failures on your PF curve, they're going to be down closer to the bottom where we could actually touch them, where we get close to the human senses. But again, an excellent technology for electrical, excellent technology for mechanical, because we see things at a very early stage. So again, I don't want you to misinterpret that it's not a good technology, because it is, but it's farther down the failure curve when you find the failures. Now, another technology here, vibration analysis. Sometimes we hire vibration technicians, and we're looking at their data, not understanding what they're doing, but this technology, operated by a trained technician, operated in the right way, finds a lot more failures than any of the other technologies. It gives us more details about them. But one of the things you have to remember about vibration analysis is every component in your plant has some natural frequency. We'll look at a slide here in a second so you understand what I'm talking about. But it's key in your equipment with vibration analysis to get some baseline frequencies, especially when the equipment's new or rebuilt. And then you kind of monitor that over time. So some people will say, well, I don't want to do vibration analysis because I don't have any baseline. Well, your baseline is probably going to be the very first test you run. I don't care whether the equipment's a month old or 5 years old. You're developing a baseline as soon as you put the tool on there. But this tool sometimes right away tells you what's going on with that equipment. So here's what I mean by natural frequencies. Let's say you have a centrifugal pump, and that centrifugal pump has 5 vanes on the impeller. Well, on my vibration report, I'm going to see a spike at 5 times RPM, which means every revolution, I've got a little spike from each one of those vanes in the impeller. In the lower left-hand corner, if you have a fan that has 6 blades on it, when I put my vibration meter on there, I'm going to see a spike at 6 times RPM. Sometimes an electric motor, depending on how many rotors there are in the motor, you might see those spikes at that many times RPM. So again, it's understanding what is the natural frequency, what's that natural vibration that's going to come off of those units, or what am I going to see in my vibration report? Well, a lot of times it's knowing how your equipment's built and what are the components in the equipment. So here's some general rules of thumb. If your vibration analyst tells you that you've got imbalance at 1 times RPM, which means this imbalance is occurring once every revolution. So at an 1800 RPM motor, if the rotor's out of balance, you're going to see it at 1800 times a minute. But you're going to see it at 1 time every revolution. So that's usually at 1 times RPM, it's going to be an imbalance situation. If you see misalignment at 2 times RPM, which means it's happening twice per revolution, that's going to be, in the case of a coupling, it's going to be misalignment, because that actual misalignment is happening twice per revolution. Or it could be a bent shaft. If it's a bent shaft, you'll see it at twice per revolution. And then at 3 times, it could be something like looseness, loose bolts, loose base, crack base. Could be resonance. So there's different frequencies that the vibration is going to tell you what's going wrong. But whenever I see imbalance at 1 times RPM, I know it's an imbalance situation in 90% of the time. So that's what I'm going to go after. Well, what are the kind of things we can find? Well, belt wear and looseness, cracked gears, cavitation, shiv run out, oil whirl. Vibration analysis is so sensitive, it can tell us which bearing is bad. And it can also tell you whether the wear is in the outer race, inner race, or in the ball pass or roller pass. That's how detailed the information can be. We can tell if we got bent shafts, chain looseness, bearing bore problems come up a lot of times on vibration analysis. Excuse me, resonance is vibration transmitted from some other component at a different frequency. It might be translated or transferred into your component and may make the readings bad, which is called resonance. It can tell us which gear is bad. Motor rotor pass, so lots of things vibration analysis can tell us. But look at the effects of vibration on the reduction of bearing life. So if you look at the left-hand column here, it says here if we can reduce vibration by 10%, it increases bearing life, ball bearing life by 37% and roller bearing life by 42%. It says here if we decrease vibration by 25%, look what it does to ball bearing life. 137 times more life. Or on roller bearings, 161 times more life. So what this is saying, a lot of times bearing wear is directly due to vibration. So again, we have to look at what our components, and that's why Cargill, and DeFosco Steel and a lot of your major reliability companies, NASA is another example. They set balance standards for all their new and rebuilt equipment. So if you take the example of new electric motors, the best electric motor for balance that's made in the industry is Toshiba. They balance every rotor and every electric motor to 0.05 inches per second or less. Or all the other motor manufacturers, they balance rotors to 0.08 to 0.12 inches per second. And many times in testing new electric motors, I found brand new electric motors that the balance standard out of the crate, the balance on I'll give you an example, it was a 150 horsepower Reliance motor. When I took it out of the crate and ran the balance on it, it was 0.28. It was 2 or 3 times over what the ESA standard was supposed to be. And how do they get away with that on new electric motors? Because none of us check them. But again, if we balance an electric motor, or even when you send the motor in for rebuild, one of your specifications to the motor rebuild shop is, I want the rotor balance to 0.05 inches per second or less. And they can do that. The equipment's at the motor shop to do that. Most of the time they don't do it. Most of the time they don't even check it because we don't ask for it. But if you do that balance standard, your bearings in your electric motor are going to last this percentage longer. So what kind of things will we use vibration analysis on? What about machines that require expensive, lengthy, or difficult repairs if they break down? We definitely want to have that equipment vibrated correct or in a low balance rate. Machines that are critical to production or general plant operations. Machines that are known to frequently suffer damage. Machines that are being evaluated for reliability. Machines that affect human or environmental safety. So what this gets down to, and we talked about this I do this with a lot of companies when we do asset criticality. All your top 10 or 20% of your critical equipment, we should be checking vibration on a regular basis or getting it balanced to some real low balance level. And what it does, it lengthens the amount of time that component's going to last. It increases that component's life cycle. So balance is critical in equipment life. And balance is what causes a lot of the vibration. Okay, motor circuit evaluation. This is a technology that, in the last 5 or 6 years here has really come on. So 2 major companies, PDMA, which makes the one in the little briefcase type unit there in Florida, All-Test Pro, company on the East Coast, but both of these tools right here are used for testing electric motors. And we can test the electric motors whether they're online, running in your plant, or we can test the spare motors on your shelf to tell if they have faults in them before you even put the motor in. So these are 6 major fault zones: power quality, power circuit, insulation, stator, rotor, and air gap. We can all check for failures with these technologies on motors, like I say, spare motors and motors in operation. So offline testing. can be used to test spare motors and verify that your motor rebuild shops actually rebuilt the motor correctly. In testing 240 motors at a facility, their spare motors, we found out about 40% of the motors at that facility wouldn't have lasted a year if they put them online. Many of these motors had been at the motor rebuild shop and been rebuilt, but poor rebuild standards. The company I work for used this equipment to test their motor rebuild shops. They were using 106 motor rebuild shops across the U.S. Only 6 of the shops passed the audit because they weren't doing some of these procedures. So again, sometimes we demand that the motor rebuild shop buy this equipment. If you're testing online while the equipment's running, you can open up your MCC box, or you can put a plug on the front of your MCC box. You can test the motor while it's in operation. Now, sometimes when that happens, of course, there's some safety precautions to do that. We can tell if we've got failures in the motor while it's running, but sometimes those failures could be in the conduit or in the junction box. So we still may have to go test the motor, take the wires off and test the motor at a later date. But again, very, very good equipment. Here's just an example. If this is what a motor 3-phase of electric motor should look like here on the bottom. So nice smooth curves on all 3 phases. Well, this motor up here has some flat spots, which says there's a broken rotor bar or defective rotor bar in that motor at 2 different locations. Very common on motors that have been rebuilt, or if you're rebuilding them at your facility, changing bearings, to have damaged or defective rotor bars. A lot of your cheaper motors like Marathon and Baldor motors have these rotor bar defects in them from new. So now with this equipment, we can tell if we have an issue. But again, I put a couple pages. These are all the things that can be checked with motor circuit evaluation. Lots of different things we can check here. You can see here, and again, I'm not going to go over these all today at the training, but lots of things we can check with motor circuit evaluation. So we can tell if the rotor's in the center of the stator. We can tell the bearing bore condition. We can tell the condition of the insulation and the windings. Lots of failures we can find with this equipment. And again, where do you check it? In Cargill, we had this green area. We wanted to check it as close to the motor as possible. But then we found out in this here, after we check it here, looking for failures, we can go back behind the fuse, or we can go back behind the disconnects. And we can find failures such as loose cables, corroded fuse clips, corroded contacts. The tools can be used to find a lot of things in your breaker box. And they can also be used to check for failures in VFDs. So again, lots of uses for the tools. Now our last one here before we wrap this up, non-destructive testing. So this is all these tests we can do for testing our stationary equipment. Liquid dye penetrant, magnetic particle, ultrasound, radiography. And we're not going to have time to go over all these today, but these are technologies for testing your stationary equipment. All the different tools from liquid dye penetrant all the way up to nuclear sources to test for failures, test for cavities, thin pipes in boilers, all kinds of things we can do with these technologies. And again, like I said, we don't have time to cover all these today, but again, I'll give you one example, liquid dye penetrant. A customer of mine is an aluminum recycler. They actually pick up these 30-ton vats of aluminum and take them down through their plant. Well, about 5 years ago, one of the eyes broke off the vat. And that's because they weren't testing them. So now every month they test the eyes on the totes with liquid dye penetrant. They test the crane or check the hooks on the crane to make sure there's none of these microscopic cracks. And so again, lots of techniques that can be used for this equipment. But again, what are you going to use? I mean, here's a little example of a mapping technology here, where we have our different components on the side. What technologies can find failures in these components. And then we pick out maybe 1 or 2 that's going to have the most benefit for the way we run our plant or what we're looking for failure modes. Again, helping you map out what technology should I use on my different equipment components. So again, steps to map failure modes to predictive tools. Perform an asset criticality. You have to know what the top 10% of your critical assets are. We're going to do this training. We have some software in our company that actually helps you do that. Determine the major failure modes you're trying to find for the equipment types. How can the bearings in my plant fail? How can the motors in my plant fail? And then pick the technology, help to find those failures. But again, you're always picking a technology looking for a specific failure mode. We have some versions of RCM and different things like that that are very cost effective to help you figure out what technology you should be using. Determine if the failure will cost more than the cost of failure. So, if you don't use a technology, if it's a $25 pump in the corner, we shouldn't be checking it with a technology. because the cost of failure may not be very high. Make sure you have your technicians are trained. It's like a few years ago, I used to tell people don't buy the MCE, the motor circuit evaluation testing tools, unless you got an electrician there who knows how to read the data. Well, now these companies do the training online. You send the results to them. Anybody can go out and take the readings. They tell you what's wrong with your electric motors. They tell you what's wrong with your switchgear. Make sure the technician that's using the tools know what they're looking for. And again, the key thing down here in the red, react to the data. If that data tells you you've got a coupling misaligned, align that coupling. If you look at this perceived world-class model, it says that this is the amount of time your maintenance people should be spending about 47% of their time doing preventive work, 35% of their time doing predictive work, and you should get your reactive work down to 18%. So that's perceived world-class. Look at this work distribution model. 15% of your labor hours should be dedicated to doing PMs. 15% of your labor hours dedicated to fixing items found during PM inspections. But look down here, 15% of your labor hours should be performing PDM inspections. But 25% of your labor hours correcting issues found from PDM inspections, which means we should be finding more things with PDMs than we find with PMs. And then it says 30% of our labor hours doing proactive tasks. Well, this is one of the things that's missing on this work distribution model is reactive maintenance. Now, you can never get it to zero, but the point of this is we need to drive reactive maintenance down to the lowest possible number. World class is 18%, or it's actually 20% at most companies. That's how you get there, making sure you get effective PMs done and predicting failures before they happen. So again, that concludes our webinar for today. If there's any questions, Justin can open it up and we can ask questions on the side here. Or again, here's the email address. Feel free to email questions that you have about this presentation. If there's more information you need, or if you need a different webinar for your company on these different tools, we can set that up for you in the future. All right, so if we don't have any questions, again, the webinar is going to be available in a PDF form. Justin has recorded the session. If you want to download the recording to play for some of the other people at your facility,